glowing data packets moving freely inside this container environment. By default, Kubernetes places no restrictions on internal network traffic. Every pod you spin up is given a direct, open network path to every other pod in the cluster. Here is a map of a standard 3-tier web application running on a Kubernetes cluster. We have a front-end pod handling user traffic, a back-end API processing requests, and a Postgres database storing the actual records. We also have a simulated attacker pod running in the exact same cluster. Because of those open defaults, this map reveals a massive security risk. The attacker pod has a direct line to your sensitive database. It is a common mistake to think that a Kubernetes service acts as a firewall, or that putting your database in a separate namespace provides network isolation. Services only route traffic, and namespaces only organize resources. Neither mechanism blocks a network connection. Over the course of this session, we will migrate from this open environment to a strictly locked-down system. We will use Kubernetes network policies and Cilium to explicitly restrict who can talk to whom. If you leave the internal network open, any single compromised pod immediately gains unrestricted access to your entire backend. Securing your outside perimeter is useless if bad actors have free rein once they get inside. Before we build our defenses, we must first verify the vulnerability. Instead of using a standard web browser, we will use the command line tool kubectl exec to simulate traffic and test exact communication paths directly from inside the pods. This terminal shows our attacker pod executing a simple curl command targeted at the database. The successful connection confirms our critical data is entirely exposed to any pod on the network. To fix this, think of every pod as a room with 2 doors. One door controls traffic coming in, which we call ingress. The other door controls traffic going out, known as egress. Our first step is to apply a baseline deny all network policy to the entire namespace. This single policy immediately locks every door in the cluster, completely severing all internal communication. Operating from this zero trust, completely denied state ensures that no accidental connections slip through. Going forward, operators must explicitly justify and configure every single network path they want to allow. This diagram shows our 4 application components again, but now every single pod is locked down. We will systematically rebuild our application's communication path, starting at the edge with the user-facing front-end pod. The front-end pod does not receive internal traffic from other pods, so its ingress door stays locked, but it needs to send user requests further down the chain. We unlock the egress door so the front-end can send requests to the back-end API. Next, we move to the back-end API pod. This middleman processes data between the user and the database. To accept incoming front-end requests, we unlock its ingress door. The back-end then queries the database, so we unlock its egress door. Any service sitting in the middle of a communication chain requires exact configurations for both its ingress and egress. Missing either rule breaks the entire application flow. Now we reach the final, most sensitive tier, the Postgres database pod. We open its ingress door to receive the backend's queries. A database never initiates calls to other pods or the internet. Therefore, its egress door remains permanently locked. With our rules securely in place, we will test the cluster again, using the exact same command line simulations we ran earlier. Looking at the top half of this terminal, we see a successful HTTP response. This confirms our allowed traffic is flowing smoothly from the front end to the back end. But when the attacker attempts to execute that same database connection from earlier, the request completely times out. Blocking the attacker's inbound connection is a standard defensive measure, but locking the database's outbound door guarantees that even if a bad actor finds a way in, they cannot exfiltrate your data back out. This diagram illustrates our final architecture. Data now flows exclusively through this single authorized route, from the front end to the back end and into the database. The attacker pod is completely isolated, unable to communicate with any other resource in the cluster, and entirely neutralized. The golden rule of Kubernetes networking is straightforward. Lock every door with a deny all policy first, then explicitly open only the exact paths your application needs to function. To execute this, you write the rules using network policy. Cilium, acting as your network plugin, enforces those rules deep in the operating system. Understanding this 2-door methodology, controlling what enters and leaves a pod, is the exact step required to turn a vulnerable learning environment into a production-grade infrastructure.
Master DevOps and cloud computing. Transition into DevOps and structured path. Track your path forward. And structured path for class.